Here's another example. We're going to find the mass of the lamina that consists of this semicircle, x squared plus y squared equals 4 in the first and second quadrants. So this is the picture of it. And the density at the point xy is proportional to the distance from the origin. Now when you say distance from the origin, the distance, if I have a point xy, let's say right here, how far is that point from the origin? You'd say, well, it's the square root of x squared plus y squared from the Pythagorean theorem. So our density function is k times the square root of x squared plus y squared. So now we'd want to set up this integral to calculate that mass, right? And like I say, it could be an amount of charge. From the field of electricity, you'll see a lot of problems like this. So here is the density function. Here's the dA, the dy dx is the dA, and we got limits 0 to square root of 4 minus x squared. I hope you understand. That's the upper part of the circle, right? That's the upper semicircle. And x going from -2 to 2. And so this would give us the mass, or it could be the total amount of charge on a plate, or whatever it would be. But this will give us the mass, but I want you to examine this integration. It doesn't look very pretty. Integrating this with respect to y, I'd have to use a trig substitution. You know, something like y equals x times tangent theta is the only thing I can think of. And you can probably imagine that's going to go down a road that's not very pretty. And when I do that, man, I'm going to have to do something with these limits of integration then. Oh! All right, enough. Because if we convert this to polar coordinates, it's not a bad problem at all. The dy dx converts to r dr d theta, right? R dr d theta. This square root of x squared plus y squared, well, that's what r is. And k is our constant, as it was before, but now this is the interesting part. Our r, if we remember drawing a ray from the origin outward, our r hits at r equals 2 all the way around here and stops at the origin, so our r limits are from 0 to 2. And since it's only the semicircle and not the whole circle, if it's the whole circle I'd go 0 to 2 pi, but it's only the semicircle, so my theta limits are 0 to pi. And now let's just integrate this polynomial, actually this power function even. So talk about nice and easy. So we want to evaluate r, integrating this, r cubed over 3, keep in mind k is a constant, so r cubed over 3, r going from 0 to 2, when you put in 0 you get 0, so put in 2 you get 8/3. So you get, sorry, when I make these at home I sometimes have to answer the phone. Okay, where did I leave off? 8k over 3 from the 8/3 times k, d theta, theta going from 0 to pi, well that's too easy. 8k pi over 3. Very nice. Very easy problem in polar coordinates.